This is the last lecture of week 5, and in this lecture we are going to discuss about the economics of electricity supply. Let us start with the concept of the load curve that we had already discussed in the context of electricity demand. So if you can recall, this is how the load curve looks like. This is the different time point of the day, and this is various, the consumption at various time points of the day. Now this particular load curve is constructed for one household. However, we have seen that you can also construct the load curve for a particular area or a number of households and so on. Or you can also construct it for a year. Now, the economics of electricity supply or production of electricity with the help of fossil fuel actually begins with the concept of load curve. Why? This is because we have already come across that the load is not the same during all the hours of a day or over a time period, or it also varies across different seasons. So there is a variation of electricity demand at different time point. Therefore, the number of generation units and the quantity of power, which is measured as kilowatt, and the energy that is measured as kilowatt hour generated by each generation unit actually varies. So each of the generation units in a power plant, they generate different amount of electricity at different point of time. What if they do not do so and they keep on producing the same amount of electricity which is required to support the peak load? This also we have discussed, and we have seen if all the generators are running in the capacity in order to supply energy which is required to support the peak load, then during the off peak period there will be high supply of electricity with very low demand. So there will be a lot of electricity which is being generated will actually be wasted, and this also have implication for the running cost. So you are incurring a running cost which is not fetching any revenue, and it's a complete waste. And you also have to think about it in this way, that this electricity that we are discussing, it's coming from a non-renewable resource, and therefore the depletion premium is going up. And not only that, it also leads to a lot of carbon dioxide and equivalent emission. So you really do not want to produce electricity when this is not required. So we cannot keep all the generation units running at a scale where it can support the peak load. The other alternative could be to run all of them at a very low rate. Okay, but if all generation units run to supply lower power and lower energy at a time, the operating cost may become very high because there will be very low capacity utilization and the poor thermal efficiency. Therefore, we have to find out some sort of a solution which is midway, where not all the generating units are working at a full-fledged, neither all of them are working at a very low capacity. So there has to be some kind of an optimum solution. In this context comes the notion of dispatching. So what is dispatching? Dispatching is a perfect case where you need to understand both the electricity sector as well as the economic context. So this is where the interdisciplinary work takes a place a lot in the context of economic dispatching of electricity. Now, what is dispatching? This actually refers to the optimum supply schedule by each of the generation units in a power plant in order to meet the total demand at a particular point of time at the minimum cost. So there are three things that we are saying. First of all, what is the amount of electricity that each of the generators will produce and supply? This is the first decision that you need to take. The two constraints that you have, one is it has to be a minimum cost one, and the second is it should be able to generate and supply the power as much as required to satiate the demand at a particular point of time. So that is the economic dispatching. Majorly there are two types of dispatching discussed in the context of energy economics or the economics of electricity sector. One is called the merit order dispatch and the other is called the incremental cost dispatch. You can also think about it as the marginal cost dispatch. So incremental cost and marginal cost, they can be used interchangeably at a conceptual level, although it is called the incremental cost dispatch. Let us first have a look at the functioning of the merit order dispatch. What does it do? Suppose there are n generating units in a power plant, which we are denoting by G1, G2 up to Gn. If we consider fuel to be the only variable input of production, although there may be other variable inputs of production, for example, raw material, labor and so on. But for the time being, let us consider that fuel is only the raw material. So coal or gas or oil, these are the only variable costs that the electricity generation sector has to incur. In that case, the average variable cost of this plant will be given by the hourly fuel cost per megawatt hour. So in order to generate 1 megawatt hour, what is the hourly fuel cost that the plant has to incur? So this is given by average variable cost. Now we actually rank the generating units based on their average variable cost, and we assume that AVC1 is less than AVC2, and which goes on, and in the ranking AVCN comes the less at the least. So the first generating unit, it has the least average variable cost of production. The second generation units has the second lowest average variable cost of production, and the nth generation unit has the highest average cost of production. If that is the case, then under merit order dispatching, generator 1 will be first loaded, and it will be operated up to a point which touches the upper limit of power generation capacity of generator 1. So generator 1, which has the lowest average variable cost, will start working, and it will work up to the point where it touches the maximum capacity utilization. So this is the first thing. Now if generator 1 cannot meet, the total demand generated at that point of time, then generator 2 will be loaded and on. This way you keep on adding generator one after the one in a sequence, so that you use the generator with the least variable cost first and the generator with the highest variable cost last, so that up to the point at which you actually meet the total supply, actually meets the total demand. Now what is the problem with this approach? This is sort of a static approach, and this does not ensure that the cost is minimized. The other problem is that when we are doing this, we are sort of assuming that at every level of production, the cost is going to stay unchanged. The cost structure, the marginal cost is going to stay unchanged, which may not be the case. So although merit order dispatch is followed in some of the cases, it's unable to deliver the optimum outcome both financially and efficiency wise. So what is the alternative to merit order dispatch? The alternative to merit order dispatch comes in the form of incremental cost dispatch, where the decision is taken based on the marginal cost of the generating units. Now, incremental cost, as I said, actually implies the marginal cost of a generating unit, that is the cost of producing an additional unit of electricity. Now, when we are talking about the marginal cost, you may remember the discussion that the marginal cost is determined only in terms of the variable cost. So when I am increasing the production of electricity, it's only the variable cost of production that is going to go up. Nothing is going to happen to the fixed cost of production. So the fixed cost of production is not going to change, while there will be an increase in the variable cost of production, which will increase the marginal cost. So what can be different variable costs? In the previous case, in case of merit order dispatch, we only considered the cost of fuel. But in this case, along with the cost of fuel, we will also consider the cost of other variable inputs. For example, labor, raw materials, several services, and so on. Now, let us come with the notations that we are going to use. Suppose Qi is the power output from generation unit I. Now, when you look at the textbooks, you will find that in most of the cases, the power output of a generation unit is usually denoted by Pi. That is also the case in the context of electrical engineering literature. However, we are not writing it as Pi here because we have used P as a notation of price. So you may get confused, and therefore we are using Qi. Generally, you can think about it as the output produced from the generation unit I. So there are n generating units, so I will run from 1 to n. We next define the concept of cost. CiQi, that is Ci as a function of quantity produced, is the cost function of generating unit I. So what is the total cost of the power plant where the electricity is being generated? The total cost of the power plant is given by capital C. Here we are. So it's given by capital C, which is sum of the cost of individual plants, individual units, generating units. So capital C is equal to sum over I, Ci, Qi. The total demand is marked as D. So D is the total demand, and the information about the total demand you are getting from the load curve. This is the role of the total demand comes as a form of constraint. So your production should be such that you are able to meet total demand at every point of time. So what is the total supply of the farm? So see, ith generating unit, it's supplying Qi. So if there are n such units like that, the total generation, total power supply will be summation I Qi. The constraint is that this summation I Qi has to be equal to D. So it's okay if it is, crosses D a little bit. So if it is higher than D by a little bit, it's fine. But for this optimization problem, we will keep D is equal to summation I Qi. So what is the objective of the supplier? We again go back to the production theory. The objective of the supplier or the producer is to minimize the total cost of the power plant, which is given by C, which is equal to summation over I Ci Q, which is a function of Qi, and subject to the constraint D, that is demand, is equal to total supply, which is summation over I Qi. So this is the objective function of the power plant. So if this function is satisfied, then we will see that the economic efficiency will also be ensured. For the optimization problem, let us set up the Lagrange function in the following manner. So L is the Lagrange under consideration. We need to minimize this total cost. Therefore, the Lagrange is written as summation I Ci Qi plus lambda multiplied by D minus Qi. So this D minus Qi, if this is set to be equal to 0, that implies that the constraint is satisfied. So there will be n plus 1 first order conditions and the second order conditions as well. So what are the first order conditions? The first order conditions for this optimization problem is given by del L del Qi is equal to 0. So if I take the partial differential of the Lagrange with respect to Qi, which is in the domain of the cost function and which is here as well in the constant, that should be set to be equal to 0. So the first order derivative has to be set to be equal to 0. Now if del L del Qi is equal to 0, that means that del Ci Qi by del Qi is equal to lambda. Because if I take the derivative of this, see, if I think about C1, suppose I am considering the first production unit. In that case, I have C1 Q1 here. So I have C1 Q1 plus C2 Q2 plus Cn Qn here. But I am taking the derivative only with respect to Qi. If I take Q1, so if I take the derivative with respect to Q1, then C2 Q2, C3 Q3, all of this, they are constant. So what I am differentiating only is C1 Q1 if I am taking the differentiation with respect to Qi. So I have the first order condition, which is given by del L del Qi equal to 0, which means del Ci Qi del Qi is equal to lambda. Because this, see, I am getting this del Ci del Qi minus lambda equal to 0, and therefore I am writing this expression del Ci Qi del Qi equal to lambda. Now I have actually n first order conditions because this first order condition holds for all n running from for all I running from 1 to n. The n plus 1th first order condition is given by del L del lambda is equal to 0, which means your D minus summation Qi is going to be equal to 0, which means that your constraint is satisfied. Now observe, when I am writing this del Ci Qi del Qi, what is this? This is the increase in the cost of production for the ith generation unit, where there is 1 unit increase in the production. So this is basically the marginal cost of the ith generation unit or ith production unit. Thus, if you see, if you need to satisfy the second order conditions, what do I need to have? I need to have del 2L del Qi2 is So I'm minimizing the cost, so that should be negative. If that is negative, that actually tells you that the slope of the marginal cost curve has to be positive. So your marginal cost has to be upward rising. So this is the same kind of condition that we discussed when we were discussing about the producer's supply behavior. So the second order condition typically is associated with the fact that the marginal costs are rising. Therefore, if you look at the first order conditions, you will see that all this marginal cost, so marginal cost of all the generating plants, we are coming here. So if I just can put a mark, so you see this is the thing. So if the marginal cost of all generating units are equal to lambda, we are saying that the optimum allocation or the optimum decision is achieved where the marginal cost of all the units are equal. So that is the point of generation, given the constraint that the demand is met. What does that mean? We have these three panels. In the first panel, we are talking about the first plant. Suppose there are two generation units, right? So this is the first unit, and here in the second panel, we are plotting the the generation of the second unit, and in the third one, we are going to plot the add up result for unit 1 and unit 2, the added up result over quantity. So how does it go? See, this is the marginal cost of the first generation unit, and suppose this is the marginal cost of the second generation unit. Clearly you can see that the marginal cost curve for the second generation unit is actually flatter. So in order to produce the same amount of electricity, the cost that the second unit, the variable cost, the second unit is going to incur is less than that of the first unit. So in terms of the variable cost, the second unit is more efficient as compared to the first unit. Now we'll see how the dispatch decision will be taken. Now if I add up the marginal cost 1 and marginal cost 2, I get the supply curve of the market, which is the added up MC1 and MC2 over quantity. Okay, so this is the supply schedule in the market, and these broken lines MC1 and MC2 are the supply schedule of individual generating units. Or you, instead of saying this as a supply schedule of market, you can also say that this is the supply schedule of the power plant, which consists of 2 units. Now suppose the power plant has to supply this much of Q1 plus Q2. This is the total output or electricity the plant has to supply in order to meet the demand. If that is the case, then the marginal cost that the plant is going to incur is captured by this horizontal line. So by the profit maximizing or by the the optimization condition that we have looked at, we have seen that at the point of supply, MC1 has to be equal to MC2. So what we are going to see is that if this is the level of marginal cost, how much does the first unit produce at this marginal cost and how much the second unit produce at this marginal cost. So the first unit will produce Q1 amount of output given this marginal cost, and the second unit will produce Q2 amount of electricity given the marginal cost. So adding up this Q1 and Q2 by the construction, what we are getting Q1 plus Q2. So the total output Q1 plus Q2 is divided among the first generation unit and second generation unit based on their marginal cost curve schedule. Now if you look here, you will see that we already have said that the second unit is probably more efficient. This second unit is probably more efficient as compared to the first unit, and therefore you see whatever is being produced by the second unit, so this much, okay, this is much bigger than what is being produced by the first unit, so this much. So the the generation unit with lower marginal cost will actually produce more. So this is the observation from here in case of a simple incremental cost dispatch problem. So you equate the marginal cost of all the plants and you equate the marginal cost of all the generating units, and therefore you determine the supply accordingly. So let us have a quick look at one of the simple problems on optimal load dispatch. The problem goes on like this. The cost function of two generating units G1 and G2 are given as follows. So the costs are measured in terms of rupees per hour. So remember this is rupees per hour. Okay. How does the cost function look like? So C1Q1 is the cost function for the first generating unit, and C2Q2 is the cost function for the second generation unit. For the first generation unit, the cost function is given as this one. So this is given as 0.5 Q1 square plus 10 Q1 plus 20. So this has a quadratic form. The second cost function of the second generation unit is given by 0.4 Q2 square plus 14 Q2 plus 25. You can quickly do some kind of a calculation in order to see what is the shape of marginal cost, what is the shape of average cost, what is the shape of average variable cost, what is the average fixed cost, and so on. And can also do a play around a little bit to see what are the shapes of these different curves. However, coming back to the problem, so the total demand that this plant has to meet through these two generation units is Q1 plus Q2 is equal to 400 megawatt. So this is the total amount that the plant has to produce. Now the question is how the plant is going to distribute this 400 megawatt between the first generating unit and the second generating unit. Let us start with the problem of optimization that we have been discussing. The optimization problem is to minimize C1Q1 plus C2Q2, that is the total cost, subject to the supply constraint D is equal to Q1 plus Q2 equal to 400. So let us see how does the first order conditions look like. So in case of the first order conditions, we have seen that the marginal cost of the first generating unit will be equal to the marginal cost of the second generation unit. So this is the marginal cost of the first generation unit equal to the marginal cost of the second generation unit, which is equal to the Lagrange multiplier lambda. Now, one thing it's important to notice that when we were talking about total cost, we were measuring it in terms of rupees per hour. Okay. When we are talking about marginal cost, we are actually talking about rupees per megawatt hour. So, and the second first order condition is given by Q1 plus Q2 is equal to 400. This is derived by setting del L del lambda to be equal to 0. The second order conditions are satisfied because we can see that the marginal costs are rising. This again, this small calculation you can do. You can derive the marginal cost functions from here and then take the derivative of the marginal cost functions with respect to Q1 and Q2 and see whether that is rising or not. Coming to so here you see I have to calculate the marginal cost for the first and second generation unit, and I have to set them to be equal to lambda. So let us first have a look at the marginal cost curves. So this is the cost curve of the first generation unit and this is the cost curve of the second generation unit. From this one, from C1Q1, we derive the marginal cost, which is MC1, that is del C1 Q1 del Q1. This is equal to, so 2 multiplied by 0.5 into Q1. So this is Q1 plus 10. So because I am taking a derivative with respect to Q1, this becomes 10, and since 20 is constant, it goes away from the marginal cost. Now you may also notice that when I am writing a cost function in this manner, this 20 is the cost which does not vary with the level of output. So basically 20 is the fixed cost of production. Now you see when I am calculating the marginal cost, this fixed cost 20 has no role to play here. So it's only the variable part that plays a role in determining the marginal cost. Similarly, if you calculate the marginal cost of the second generating unit, the MC2 is given by del C2Q2 del Q2, which is equal to 0.8. So 0.8 I am getting from here, this 0.4 multiplied by this 2, and therefore I am getting 0.8 Q2 plus 14. This Q2 goes away and this 25 disappears. So these are the two marginal cost curves given for the first generating unit and the second generating unit. Also, what I have, the third condition, optimality, first order condition that I have by setting del L del lambda to be equal to 0, that Q1 plus Q2 is equal to 400. Or I can express Q1 in terms of Q2 by writing Q1 is equal to 400 minus Q2. So at optimum, what is happening? At optimum, I know that MC1 is equal to MC2, which is equal to lambda. So the plugging the values from here, if I plug the values from here and I plug the values from here, what I get? I get Q1 plus 10, that is this value, Q1 plus 10 is equal to 0.8 Q2 plus 14. So this is 0.8 Q2 plus 14. So this is one equation that I have in terms of Q1 and Q2. By just changing this, so this is the relationship between Q1 and Q2. Now what I am doing, I am plugging this relationship, that is Q1 equal to 400 minus Q2 here. Okay, so instead of Q1, I am writing 400 minus Q2 plus 10 will be equal to 0.8 Q2 plus 14. This actually gives me, see this, so this is what, this is Q2. If I take it to the right hand side, I get 1.8 Q2. So this is my 1.8 Q2, which will be equal to 400 plus 10, that is 410 minus 14. So I get Q2, or I get 1.8 Q2 is equal to 396, or Q2 is equal to 396 by 1.8, which is equal to 220 megawatt. So the second generating unit is going to produce 220 megawatt of electricity. Substituting this value in the relationship between Q1 and Q2, this tells me that if Q2 is equal to 220, then Q1 should be equal to 180 megawatt. So I had to distribute 400 megawatt between Q1 and Q2, between the first generating unit and the second generating unit. So what I am doing is I am actually giving the second generating unit to produce more output, because the marginal cost is lower and it's more efficient as compared to the first one. After doing this, so this is the optimal distribution of load in two generating units. After doing this, let us have a quick look that whether we are satisfying the condition of MC1 equal to MC2 or not. So this is just a cross check to see whether your calculations has gone right or not. So marginal cost of the first unit at Q1, that is equal to 180, is equal to, you go back here, so you set 180 plus 10, which is 190. So the marginal cost at the optimum production is 190 for the first plant. For the second one, you have to put this 220 here. So it's 1.8 multiplied by 220 plus 14. So 0.8 multiplied by 220 plus 14. This also results in 190. So what you see that the marginal cost of the first plant is equal to the marginal cost of the second plant at the point of optimum production. So one check is done. The second is, let us also try to identify what is the total cost of producing this 400 megawatt. So the cost that the first plant is incurring to produce 180 unit of output can be derived from this C1 function. So what I am doing, I am just plugging 180 here. So 0.5 multiplied by 180 square plus 10 multiplied by 180 plus 20. So this is what I have, 0.5 multiplied by 180 square plus 10 into 180 plus 20. So this is the total cost of production of 180 megawatt. Now see, when I am talking about the total cost of production, this also includes the fixed cost as well. Similarly, I can derive the total cost of production for the second plant at the optimum level of 220 megawatt, and that is 22464. So second plant is producing more, the incurred cost is more, however the marginal cost is much lower. So the total cost that to produce 400 megawatt of power is equal to C1Q1 plus C2Q2, that which adds up this 18020 and 22464, and then you get 40485 per hour. So this is the total cost that you get. Now there are certain interesting things that you can carry on along with this example. So this is the optimum allocation. What you can also do is that you can check what will be the total cost under merit dispatch. So in case of merit dispatch, what do? You have to set some capacity for both the plants, and you run the second plant up to its full capacity if it is less than 400, and for the remaining amount you run plant 2, and then you see what is going to be the total cost. You can also check if you want to distribute the generation in the equitable fashion. So both the generating units will produce 200 megawatt, then what is going to be the cost implication? And you will find that if under merit dispatch as well as under this equal distribution, the total cost of generation of the same amount of power will be higher than this 40,484 per hour. Okay. Next, we move on to another concept which is called generation capacity reserve, which just follows the concept of the load dispatch. So the power plants always maintain an extra capacity in addition to what is required to produce and supply according to demand. So if my demand is 400, if my demand is 400 megawatt, then I would actually try to produce or try to be ready to produce a little more than that, because you never know when something goes on malfunctioning. Now this extra capacity is called the generation capacity reserve. So this is like a buffer, this is like a cushion that you have, that you can use when it's needed. If it is not needed, you don't use it. Now this generation capacity reserve actually comes in two forms. One is called a spinning reserve and the other is called the quick start reserve. What is spinning reserve? This is particularly important in case of fossil fuel based electricity generation. So all the generation units of a plant, they are not engaged in production at every point of time. So some generation units are loaded, some generation units are not loaded. Now if I take off one generation unit because there is not much demand or because of maintenance, then once the demand arises, immediately I cannot run that generation unit. It takes at least 8 hours to run the generation unit. And also this shutdown and restart, it has some costs associated with it. Therefore, if I completely shut down one generation unit and then there again restart it, it not only costs some money because of this restarting, but it also costs some amount of time. So it cannot be, if I feel that the load is coming, I cannot immediately switch on the generator and start generating electricity. I need to have some time. Therefore, what happens? Therefore, the power plant, what it does, it actually runs more number of generators than it is required at a very low capacity. So some generator will work to a higher capacity. Some generator as a buffer will be on but will work at a low capacity. So this kind of a buffer, this safety margin that the power plants keep, is called the spinning reserve. The second one is a quick start reserve. This is often observed in case of hydropowers. So these are plants which could be started up very quickly. So it's not like a boiler where you really need to you take like 8 hours to restart it. The second type of generation capacity reserve that you have is called the quick start reserve, and this is often noticed in the context of the hydropower. So these are plants which could be started up quickly to deliver the load and meet the demand. Some hydro plants do have this kind of mechanism and can start functioning in a very quick fashion. So you don't need to wait for 8 hours. Gas turbines can also operate in the similar manner. However, in case of this quick start reserve, there is always a risk associated if the generator unit doesn't start. If there is malfunctioning, then what happens, right? So oftentimes it's said that the spinning capacity reserve is a much reliable option as compared to the quick start reserve, although you can see that they are often utilized in a very different context or with respect to different technologies. The optimal load dispatch problem becomes a little bit complicated if you think about the spinning reserve. So now it's not only the equalization of marginal cost, but you also have to ensure that all the plants, under consideration, those who are supposed to run, they have to run in a minimum load. So you have some additional problem and you have to cross check a couple of things. So the problem goes on in this way. Now I have added one more generating unit and the cost function of these generating units are given as follows. So C1 is the first generating unit, the cost function 0.4, Q1 square plus 10 Q1 plus 25. The second generating unit has cost function C2 Q2, which is equal to 0.35 Q2 square plus 5 Q2 plus 20. And the third generating unit has C3 Q3, which is equal to 0.475 Q3 square plus 15 Q3 plus 25, 35. Again you notice this 25 here, this 20 here and this 35 here, they all are fixed costs of production and will not be reflected in the marginal cost. In order to keep the spinning reserve, the condition goes on like this. All three units, they have to run and continue producing a minimum output of 30 megawatt per hour. So this is the minimum requirement. So in order to keep the spinning reserve, all these three generating units, they have to keep on producing 30 megawatt per hour. Now how do we, this 30 megawatt per hour has come? This is generally determined based on the the thermal consideration of operation of the boiler. So these are some technical specifications. So you cannot run it at the capacity less than 30 megawatt per hour. Probably then the operation cost will go up, and physically that is not quite possible. We haven't added information, but in this problem probably will not need it, but in some cases you need it as well. So the maximum generation capacity of these three units are 500 megawatt, 500 megawatt and 250 megawatt respectively. So the first two units are relatively bigger, where the third unit is relatively smaller. Now the question is that if the total demand that you need to meet is 200 megawatt, how will you distribute the load? What will be the load dispatching when you have this added condition of that all three have to run minimum at 30 megawatt per hour capacity? Let us have a look at the marginal costs first. So these are our cost function that I have already said. So these three are the cost function. From them taking the derivative, we get the marginal cost functions. So by taking the derivative of C1 with respect to Q1, taking the derivative of C2 with respect to Q2, and the derivative of C3 with respect to Q3 give us the marginal cost functions MC1, MC2 and MC3. So we are denoting these conditions as 1A, 2A and 3A. We also have the condition which is Q1 plus Q2 plus Q3 is equal to 200. So basically we have four equations here, but we'll see that we actually have three equations to solve in order to determine the three variables Q1, Q2 and Q3, which is perfectly possible. So what do we do? Next, what we are going to see, before we try to equate the marginal cost curves, what we are going to see, what is the marginal cost of each of these generating plants at 30 megawatt. Okay, so what is going to be the marginal cost of each of the plants at the lowest operation? So I am calculating the value of the marginal cost at Q equal to 1 for the first one, Q1 equal to 30 for the first one, Q2 equal to 30 for the second one, and this should be Q3 here. So 0.95 Q3. So 0.95, so let me just make it. So this is not 2. So 0.95 Q3, I'm setting that to be equal to 30, and I am going to see how does the marginal cost look like. The marginal cost of the first plant at output equal to 30 is 34 rupees per megawatt hour. The marginal cost of the second plant at 30 load equal to 30 is 26 per megawatt hour, and so for the third plant the same is 43.4. So if I compare this 34, 26 and 43.5, what I see that this one, so the second plant that you have, this one, here we go. Okay, so this plant, the marginal cost of this plant is lowest at Q equal to 30. Okay, so this is the most efficient plant that you have. The next efficient plant, the next efficient generating unit, so this is, sorry, so second unit is the most efficient generating unit. The next efficient generating unit is the first one, and the third one is the least efficient generating unit. As you can see that the marginal cost is highest at Q equal to 30. So the second unit is the least cost unit, as the marginal cost of second plant is least at the minimum load. So what happens is that first plant unit 2 will start operating, while unit 1 and 3 keep producing the minimum load, and it is first the second unit that will be allowed to go beyond the minimum load. So both So remember one thing, that it does not mean that the first and the third generating unit stops producing. They keep on producing 30 megawatt. However, the second generating unit is now allowed to produce more than that. Let us have this picture quickly. So notice that the diagram may not be at the scale. So the 30 here that I have depicted may be a little different from 30 here, but this gives you the general understanding of what is going on. So this is the marginal cost of the first generating unit. This is the marginal cost curve for the second generating unit, and this is the marginal cost curve for the third generating unit. You can clearly see that the intercept is lowest here, right? Followed by this, and this followed by this. This you should be able to match with the structure of the cost. This gives you the sort of the okay. So this is one. The second thing is that look at the slope. The flattest one is MC2, that is the second generation unit, because it's most efficient. Then the first plant, which is next, and the third one is the least efficient. How do we see that? We can see that if all of them they produce 30, then the minimum marginal cost is obtained here. So this is the minimum marginal cost that you have, and this is happening for the second plant. The next higher marginal cost is here for plant 1, and the highest marginal cost, which is actually quite high as compared to 1 and 2, is here. So second generating unit is the most efficient unit, followed by the first, and then followed by the third. Now see what happens. As we have said, all of them, they will start producing 30 megawatt. That is for sure. Now who will that gives you 90 megawatt. But your demand is more than 90 megawatt. So at least one unit has to produce more than 30 megawatt. Now who will do that? Of course, this is the first plant, because this is efficient. Now the question is, do you think that once this 90 megawatt is produced, the rest 110 megawatt all will be produced by the second plant, or is it going to be distributed between the other plants as well? The logic goes on like this. So unit 1 does not operate until the costs are equalized for these two farms. So unit 1 starts operating where the marginal cost of producing 30 unit is equal to the marginal cost of the second plant, whatever it produces. So what we are saying is that, see, up to this second Q2 equal to 41.2, whatever is produced will be produced only by the second unit. Okay, because if you produce anything here, then the marginal cost of the first unit will be more than by the second unit. The moment the second unit produces Q2 equal to 41.2, beyond that the marginal costs are equalized. So when marginal costs are equalized, it means that, the marginal cost that you would need to produce 30 units in plant 1 is same as the marginal cost that you need to produce 41.2 units in the second plant. Beyond that, what you produce, it doesn't matter whether you produce in the first plant or you produce it in the second plant. So the condition is given by MC1 at 30 should be equal to MC2. Now what is MC1 at 30? That is 34. So MC2 is 0.7 Q2 plus 5. So we are equating, if I can just take you back here, MC130 quickly. So you see, this is your MC130. So MC130, which is 34, and MC2 is 0.7 Q2 plus 5. So I am equating 0.7 Q2 plus 5 with this 34. Okay. So I am equating 0.7 Q2 plus 5 with 34. That gives me Q2 is equal to 41.4. This should be 41.4 here. So this gives me, or maybe this is, so it should be either 41.4 in both the cases or 41.2 in both the cases. So what you see that Q2 is equal to 41.4. Now if you think about the first phase where which gives you the point up to which both unit 1 and 3 produce only 30 megawatt, the upper production limit of phase 1 is given by Q1 plus Q2 plus Q3, which is 30 plus 30 plus 41.4. Or you can say 30 from the first unit, 41.4 from the second unit, and 30 from the third unit. So the total production is 101.2 megawatt. Now the thing is that even if you are producing at this point, it gives you only 101 and 2 megawatt. So you are almost left with some 99 megawatt. Now who will produce this 99 megawatt? So plant 1 and 2 keeps on producing unless the marginal cost of production is equal to the third marginal cost of production of the third generating unit at Q equal to 30. So unit 3 starts operating at MC equal to 3 equal to 30, which is equal to MC1 and MC2. So this is MC1 0.8 Q1 plus 10. This is being equated with 43.5, which is the marginal cost of the third generating unit at quantity 30. Also, we are equating 0.7 Q2 plus 5, which is the marginal cost of second unit, equal to 43.5, which is the marginal cost at the level of production 30. So this gives us two equations, Q1. So this is, I'm sorry, this is again going to be, sort of Q2, and this is not Q1. So Q1 is equal to 33.5 divided by 0.8, which is 41.87, and Q2 will be equal to 55. So when the third generating unit is brought into the process of production, this is this point where the second plant is producing 55 units, the first plant is producing 41.87 unit, and the third plant is producing 30 unit. Beyond that, any of the plants can produce depending on the next marginal cost. So up to 101, so if you go back to the previous one, up to 101.2, only the up to 41.2, it was only the first plant which was producing. Up to 101.2, it was only the first and second plant which one are producing, right? Beyond this 112.87, okay, so what is happening is that if you go back to the previous results, you will see that up to 41, when Q2 equal to 41.2, that is 41.2 plus 30 plus 30, that is 101.2. So up to 101.2, it was only the first unit that was only the second unit that was producing more than 30 units. Okay. After 126.87 megawatt, along with the the second, up to that it was only the first unit. After that, both the first and second unit starts producing. So between 101 and 126.87, it's the first and the second units that are producing. Beyond 126.87, all three units are producing. So always remember, when I am talking about this total amount of electricity generation, it always incorporates the 30 unit that is minimum to be generated by each of the units. So you see that if your supply has to exceed 126.87 megawatt, then all three generating units have to run in an optimum manner. So basically, it boils down to the simple sort of incremental cost dispatch problem. Had your total demand been 100, megawatt, then you would have seen that you don't need to use the third one beyond 30 megawatt. Only first and second one can go beyond 30 megawatt and they can produce. However, since the total demand is greater than 126.87, all the three plants have to run optimally. Okay. Now let us have what is the optimum load dispatch condition under the incremental costs. This is same as previously what we have done. These are the three cost functions given. From there we derive three marginal cost functions, and we also have the constraint where the demand has to be equal to supply, which is equal to 200. At optimum, we have MC1 equal to MC2 equal to MC3. So what we can do, we'll first take MC1 equal to MC2 and then we'll take MC2 equal to MC3 and try to solve the problem. Now MC1 plus MC2 implies, so this I'm getting from this one and from this one, 0.8 Q1 plus 10 is equal to 0.7 Q2 plus 5. Again, if I plug 4 here, so if I plug 4 here, then I have Q1 equal to 200 minus Q2 minus Q3. I am putting it in this condition, so I am getting 0.8, 200. So instead of writing Q1, now I am writing 200 minus Q2 minus Q3. plus 10 equal to, again getting from here, 0.7 Q2 plus 5. So this gives me 160 minus 0.8 Q2 minus 0.8 Q3 plus 10 is equal to 0.7 Q2 plus 5. So it reduces to the equation 165 minus 1.5 Q2. I am taking this Q2 here, 1.5 Q2 minus 1.8 Q3, which is equal to 0. So if I want to express Q3 in terms of Q2, then I get Q3 is equal to 165 minus 1.5. So 165 minus 1.5 Q2 divided by 0.8, which is approximately equal to 206.25 minus 1.875 Q2. So Q3, so this Q3 is equal to 206.25 minus 1.875 Q2. This is the relationship between Q2 and Q3 that we have derived. Now let us equate MC2 and MC3, the second condition. This gives me the equation in terms of Q2 and Q3, which looks like this. So I have equalized the marginal cost, and this again gives me the relationship between Q2 and Q3 in the following manner. So 0.95 Q3 minus 0.7 Q2 plus 10 is equal to 0. Now what I am doing, I am plugging this Q3, this value, this particular value of Q3 here. So what I'll get, I get 0.95206.25 minus 1.875 Q2 minus 0.7 Q2 plus 10 equal to 0. Solving this problem, what I get Q2 is equal to, so the total production by the second plant, that is Q2, is equal to 83.06. Now you can substitute this Q2 in 5. So this is, here is your 5. So this is the value of Q2 you have. You simply go here and substitute here. So you have 206.25 minus 1.875 multiplied by 83.06. So this gives you Q3 is equal to 50.51. Okay. So what I have now, I have Q2 equal to 83.06, Q3 equal to 50.51. I deduct both of them from a total of 200 to get Q1 is equal to 66.42. So at optimum, you can derive what is the marginal cost. You will see that they are approximately the same and all of them are equal to 63. So this is how the diagram looks like. So this is the production by the first unit, 66.42. This is the production by the second unit, and this is the production by the third unit, and marginal costs are equalized at 63. Clearly you can see the most efficient plant, that is the unit, that is unit 2, is producing the most, followed by the next efficient unit, which is the first unit, and the third unit produces the least amount of output. So this is in a nutshell the problem of dispatching when you have the spinning reserve on. You can, here also what you can check is that what happens to the total cost. Here you can, I haven't calculated the total cost yet, but you can calculate what is the total cost, what are the costs of different plants and different generating units. And also what you can do, you can compare this situation with a situation where you distribute the total output equally among the three plants, 3 units, and you can also see what happens to the cost under the problem of merit dispatch.